The sun tore open, Earth's magnetic shield lit up, and our only interstellar visitor slipped into blinding glare at the same moment. Then the ground shook in, far-off places. Coincidence or chain reaction? Stay with me as we pull this apart in real time and follow the clues. You felt it the instant you heard the words, fast solar wind. It sounds like weather, but it is not rain or gusts in the air. It is a flood of charged particles launched from a gaping coronal hole that straddled the equator of our star. Imagine a wound that does not bleed in color, but bleeds energy. Field lines on the sun opened outward like unlatched gates, and a river of plasma rushed down the lanes those gates revealed. On Earth, the invisible shield that protects our atmosphere braced for impact. Our magnetosphere is not a wall. It is a flexible bubble that can couple to the sun's field like two gears snapping into alignment. When that alignment clicks just right, energy transfer spikes. Auroras race toward lower latitudes. Satellites feel drag swell. Power grid managers get the kind of phone calls nobody wants to receive at 2 a.m. Now fold a second timeline on top of that. As the solar river roared, 3I Atlas reached the worst place an astronomer can imagine for a fragile target. The line of sight slid too close to the Sunday. Telescopes on Earth and telescopes in space lost contrast. The comet did not wink out because it failed. It slipped behind brilliance so overpowering that even the sharpest optics could not tease signal from glare. One moment we had a faint smear. The next we had nothing but light. Add a third line. Hours after the solar wind pressed into our magnetic field, multiple strong earthquakes struck in different parts of the world. To a human brain that evolved to spot tigers in tall grass, this looks like a pattern writing itself. The sky flares. The comet disappears. The ground moves. The mind whispers connection. The scientist in the same mind whispers caution. So, we are going to do both. We will respect the sting of coincidence and the gravity of evidence. First, the paradox that hooked you is real. 3 rare or attention-grabbing events piled into the same news cycle. Second, the known physics says tectonic plates do not listen to the Sunday. They grind and fail under stresses stored for years. That does not mean you have to switch your curiosity off. It means you aim it. Start with the Sunday coronal holes are not explosions. They are topological openings in the magnetic carpet. Through them, the fast wind can sprint at roughly 700 kilometers per second. That number is not abstract. At that speed, a particle could cross an ocean in the time it takes you to brew a cup of coffee. A trans-equatorial hole matters because it connects northern and southern magnetic domains. The result is a broad fire hose that can tangle with Earth's bubble more effectively than a small high-latitude jet. Now the comet. 3I Atlas is special because it did not form here. It was flung from another system long ago. As it falls toward our sun on a hyperbolic path, every photon that bounces off its dust and every molecule that escapes its ice is a hint about chemistry somewhere else in the galaxy. That is why losing sight of it hurts. The period near the sun is a laboratory. Activity spikes. Jets switch on. The coma thickens. Spectral fingerprints sharpen. Then geometry shuts the lab door just when we want it most. Here is the part most people miss. Going dark is not the same as dying. During solar conjunction, even healthy objects vanish. The question is, what shape returns when glare relaxes? A single steady nucleus. A string of fragments like beads. A cloud so diffuse that only spaceborne coronagraphs can see it, or nothing at all. And the earthquakes. The consensus view is clear. The link is weak to non-existent. Yet even in that clarity, researchers hunt for tiny effects that might nudge faults already on the brink. If such nudges exist, they would be marginal and statistical, not cinematic and direct. That is not an invitation to leap. It is a reminder that science is a lens you focus, not a flag you wave. So what do we do with a night like this? We build a shared investigation. We mark the calendar for when the comet should clear the sun by enough degrees to be found again. We watch space weather dashboards for the tail end of the fast stream. We follow amateur networks that can spot a glimmer before major telescopes pivot. We keep 2 truths in mind at once. The universe is under no obligation to be dramatic, and yet, sometimes it is. You will hear intriguing claims over the next few days. Secret images, hidden spectra, electrical forces rewriting the rulebook. Before we chase any of that, we will lock down what happened, when it happened, and how strong the signals really were. Then, we will ask better questions. Did the solar wind orientation truly maximize coupling? Did 3I Atlas show hints of stress before it slipped behind the glare? Are there early signs of recovery in coronagraph frames? This story will not be solved by one image or one tweet. It will be solved by a chain of small confirmations that either point to business as usual or to something we have not seen before. Either way, we win. If the comet comes back intact, we learn how tough alien ice can be. If it returns in pieces, we learn how and when it fails. If it does not come back at all, we will write a careful obituary and update the models that predict survival near the Sunday. For now, take a breath. Step outside if you can. Find the dark. Feel the scale of the thing that warms every morning you have ever had. Somewhere in that glare, an interstellar traveler is either holding together or letting go. We will be waiting when it steps back into night. Start at the surface of the sun, where there is no surface at all. There is a bright boiling skin of plasma threaded by magnetic loops that arch up and dive back down like hot suspension bridges. Most of the time, those loops close on themselves and trap particles. Sometimes the loops do not close. They open into space. Where they open, the corona thins and darkens. That patch is a coronal hole. Open lines are on ramps. Particles no longer swirl in circles. They stream outward along those lines and join the solar wind. In quiet times, that wind ambles along at roughly 400 kilometers per second. From a big coronal hole, it can roar near 700. That difference is not academic. Faster wind means more momentum, more energy, and a better chance to rattle anything magnetic that stands in its way. Earth stands in its way, but not as a brick. Our planet is wrapped in a magnetic bubble. Think of it as a windsock rather than a wall. When the sun's field, carried by the wind, brushes our field, the two can sometimes lock together and trade energy. The key is orientation. If the passing field tilts the right way relative to Earth's, magnetic barriers weaken and the transfer opens wide. The name for that handshake is magnetic reconnection. In human terms, it means the door between the solar wind and our bubble can swing open. This is why a trans-equatorial coronal hole matters. It straddles north and south solar latitudes, creating a broad lane that can sweep across many longitudes as the sun rotates. Imagine not a single fire hose, but a wide river. As the sun turns, that river washes past the line between day and night and sends sustained gusts toward Earth for days at a time. Inside that stream, the embedded magnetic field can hold a steady orientation long enough to matter. If that orientation happens to oppose Earth's, coupling spikes, and the auroral engine roars. Auroras are the visible poetry of that energy exchange. Field lines guide charged particles down into the polar sky, where they collide with atoms and molecules and make them glow. Greens from oxygen, purples from nitrogen. Cameras cheer, power operators frown. The same process stirs currents in the upper atmosphere and in long wires on the ground. Satellite orbits puff as the upper air warms and expands. Positioning systems can wobble. None of this is supernatural. It is a storm in a magnetic ocean. We can see coronal holes before they hit us. Ultraviolet images from solar observatories reveal the dark patches cleanly. Forecasters estimate when the fast stream will arrive by watching solar rotation, then watch ground and space sensors as the wind sweeps past spacecraft upstream of Earth. Density rises. Speed climbs. Magnetic orientation tips this way or that. A few numbers tell you whether the next hours will be a mild glow over the poles or curtains of light far to the south, along with a headache for anyone who runs a satellite. Here is the detail that gave our night its uncanny feel. The stream was fast and the orientation favored energy transfer just as 3I Atlas went invisible in the sun's blaze. That is a timing coincidence, not a mechanism, but it is a powerful one. When big things happen together, our pattern detector lights up. We can honor that feeling and still keep the physics straight. The wind does not reach down and shake faults underground. It does reach up and shake a magnetized sky. Zoom back in on the hole itself. It is not a crater carved by an explosion. It is a topology change in the sun's magnetic field. Picture a forest of magnetic arches. In a hole, some arches never loop back. They lean out into interplanetary space. Gas on those paths does not have to fight its way through closed loops. It escapes. That escape lowers density overhead, and the region looks darker to instruments that image the hot corona. Because the sun spins, that open patch sweeps like a lighthouse beam. Every spin of the star sends another pulse of fast wind toward the orbits in its path. Why do some holes stretch across the equator? The sun's magnetic field is a restless tangle that flips polarity about every 11 years. Near activity peaks, long open regions can span hemispheres. When they do, they can connect to the lanes of space Earth is about to enter. That is how a hole on the sun can write a forecast for our sky a few days in advance. Now connect this to your night on the ground. If you saw alerts, they came from upstream monitors that tasted the wind hours before it reached us. If you saw auroras, where you have never seen them, you are living inside a physics lesson. Space weather is not a metaphor. It is a daily background that occasionally becomes the headline. So what would we expect the fast stream to do to a comet close to the Sun? The comet has no magnetic shield. Its cloud of gas becomes ionized, and the embedded solar field drapes around it like a cloak. The fast wind can tug the ion tail, even snap it, and force a new one to grow. Those effects are real and spectacular in images. They're also secondary to what heat does near closest approach to the Sun. Thermal stress and outgassing torque are still the main actors in whether a nucleus holds together. The coronal hole explains why our sky went loud. The timing explains why our nerves did. The rules have not changed. Open lines on the Sun make fast wind. The right tilt opens our door. Lights turn on over the poles. Electronic systems feel it. Then the stream passes, the bubble recovers, and the star keeps turning. The next hole will come. We will be ready to read it. When the ground shakes after the sky roars, our pattern detector fires. Cause and effect is the story engine in the human brain. So we ask the tempting question: did the solar wind nudge Earth and set faults slipping? The short answer from mainstream geophysics is no. Tectonic plates move because of deep heat, mantle convection, and the slow build of stress along locked faults. When stress exceeds friction, a fault snaps. That cycle plays out over years to centuries. Solar, storms do not reach down and crank the crust. Let us honor the long view. Plate boundaries are machines that store energy gradually and release it suddenly. Subduction zones drag one plate under another. Transform faults grind laterally like serrated gears. In those systems, the actors are rock strength, pore pressure, temperature, and time. The magnetized gust sweeping past our planet lies thousands of kilometers above the ground in a thin, electrified layer. Between sky storm and bedrock sits a thick atmosphere, an ocean of air that absorbs and blurs whatever happens above. Still, scientists test ideas even when the odds are slim. If the Sun had any influence at all, it would be subtle and statistical, not cinematic. Researchers have combed earthquake catalogues for decades, looking for rises in quake rates during solar maxima or during days with strong geomagnetic storms. Most studies report no robust link once you account for chance, clustering, and reporting biases. A few claim weak signals in certain regions or certain fault types. Those claims spark debate because small samples and cherry-picking can fool even careful analysts. Replication is the referee. Replication is hard. What mechanisms have been proposed? One idea is ionospheric coupling. During magnetic storms, electric currents flow more strongly in the ionized layers of the upper atmosphere. Those currents induce weaker currents in the crust. In theory, that could change tiny stresses on faults or shift fluid pressures in fractured rock. The numbers are small. Imagine a mountain of weight already balanced at the edge of tipping. Add a feather. Most of the time, nothing changes. If the mountain was already sliding, a feather is irrelevant. If the mountain was hung on a knife edge, maybe a feather matters. That maybe is the entire argument, and it is difficult to test. Another idea focuses on Earth's rotation rate. Solar wind momentum can couple to our magnetic field and atmosphere, changing rotation at levels measurable only with very precise instruments. The changes are minute, far smaller than the daily tidal tug from the moon, and Sunday tidal stresses are real. Ocean tides and solid Earth tides flex the planet by small amounts. The correlation between tide phases and earthquakes has been studied for many decades. Results are mixed. Some faults with very specific orientations appear slightly more likely to fail near particular tide states. Even there, the effect is weak. The larger story still belongs to tectonics. A third line of speculation points to atmospheric pressure changes during geomagnetic storms, arguing that pressure fields might load faults a little. But weather systems move pressures around constantly, and with far greater amplitude than any storm related to space weather. If weather drove quakes, we would have seen that clearly by now. We have not. So why do coincidences feel so convincing? Because our brains evolved to err on the side of association. In a dangerous world, it is safer to connect two Russells in the grass into a tiger than to miss the one time they were the same animal. We inherited that bias. When a solar storm hits, a comet disappears into glare, and a strong quake strikes hours later, the narrative writes itself before we have even opened a journal article. Awareness of bias does not eliminate it. It gives us a handle to pull back from the ledge. There is also the issue of base rate. Earth has on the order of 15 magnitude 7 earthquakes in a year. That means, on average, a strong quake every few weeks. Space weather events also cluster during active solar years. If you slide 2 calendars across each other, some alignments will look uncanny by chance alone. The cure is math. Ask how many days with strong space weather also have strong quakes compared to what you would expect if they were independent. Then ask whether that difference persists when you change the time window or the region or the magnitude threshold. If, and the signal evaporates under those small changes, it was not a signal. It was a pattern in clouds. None of this is permission to stop looking. It is a guide for how to look. Define mechanisms in advance. Make predictions before the data arrives. Share code and catalogs so other teams can rerun the test. If a tiny effect exists, the path to finding it runs through careful statistics and patience, not through viral maps with red circles. So where does that leave us tonight? With 2 truths held together. 1. The physics of earthquakes is overwhelmingly about plates, friction, fluids, and time. 2. Nature is allowed to surprise us. If the sun whispers at the margins of fault systems, the whisper is faint. Proving it would require many storms and many quakes, and a signal that stays put when you poke it. Until then, when the ground moves after the sky glows, take a breath. Appreciate the timing. Do not marry it. Curiosity is not the enemy of skepticism. It is the engine. We can keep watching the space weather dashboards and the global seismometers without forcing a link where none has been earned. The world is full of real connections waiting to be mapped. We do not need to invent new ones to feel the thrill of discovery. Start with a simple idea. Most comets are time capsules from our own backyard. They froze out in the deep cold beyond Neptune and have been circling the sun ever since. Interstellar comets are different. They are not ours. They were born around another star, in another nursery, under another mix of light and chemistry. When one wanders through our sky, we are not just watching ice sublimate. We are holding a sample from somewhere else in the galaxy without leaving home. Think about Oumuamua, the first odd messenger that sailed through in 2017. No classic dust tail, no fluffy coma. Yet as it moved away from the sun, it picked up a tiny extra push that gravity alone could not explain. The simplest picture was outgassing of something volatile that did not make a bright dust cloud, perhaps carbon monoxide or nitrogen ices. But the truth is, we never saw the usual signature, and the data window closed fast. 2 years later came 2I Borisov. That one looked and behaved like a familiar comet, with water vapor and carbon monoxide in its spectrum, and even hints of fragmentation near closest approach to the Sunday. Together, they told us something profound. Other planetary systems can build bodies that rhyme with ours, and bodies that do not. Now step 2, 3I Atlas. A visitor on a hyperbolic path, moving too fast to stay bound to our Sunday, that speed and shape are the hallmarks of a traveller from beyond. Every photon that scattered off its dust before it slipped into solar glare carried information about an alien nursery, ratios of carbon to oxygen, clues to how icy grains clumped in a different protoplanetary disk, hints about whether organic molecules form easily across the galaxy or only under certain stellar lamps. We were not just clocking a rock. We were reading a chemical postcard from a star we will never see up close. This is why the disappearance hurts. Not because vanishing during solar conjunction is rare. It is not. It happens all the time. It hurts because the stretch near the sun is the richest part of the laboratory. Heat wakes buried ices. Jets switch on. The coma grows thick enough that spectral lines sharpen and multiply. Non-gravitational nudges from those jets make the orbit wobble in ways that tell you where the active areas live on the nucleus. When the geometry yanks the object into glare right then, you feel the door slam just as the conversation gets good. So what exactly are we trying to learn from a stranger like this? Start with composition. If the ices match our comets closely, that supports the idea that planet-forming chemistry is robust across different stars. If the mix is skewed, heavier on carbon monoxide or nitrogen compared to water, that hints at colder birthplaces or unusual disk chemistry. Then, structure. A dense, rock-rich nucleus would vent gas in tight jets and resist thermal cracking. A fragile pile of snowy rubble would shed dust easily, brighten in bursts, and be more likely to split. Spin state matters too. Jets act like thrusters. They can torque a small body into a wobble or a spin-up that approaches breakup speed. Watching the light curve flicker lets us time that spin and spot changes. There is also the question of surface history. Comets that have looped the sun many times often develop a dark crust that chokes off activity until cracks open. An interstellar object might wear a different coat. It could carry a mantle baked by cosmic rays for millions of years, then shed that skin in sheets as heat finally penetrates. If we catch it before, during, and after closest approach, we can map those transitions instead of guessing at them. Why does any of this matter beyond checklists in a journal? Because it tells us whether our story is typical or weird. If interstellar comets tend to echo ours, then the processes that built Earth and its neighbours may be common. If they often look chemically or structurally alien, then world-building is a more unruly business than our textbooks suggest. That answer informs everything from how planets hold atmospheres to how often life-friendly chemistry might arise. There is also a practical angle. Interstellar traffic is rare, but not vanishingly rare. Surveys are getting better every year. If we learn how these objects behave near the Sun, we can plan intercept missions that meet the next one in time to sniff and sample. Think of a small, fast spacecraft waiting on the pad with a menu of possible trajectories. Detection comes in. A handful of burns later, we are flying through the coma with instruments tasting the vapor. That only works if the playbook is ready. 3i Atlas is one of the rehearsals. So yes, the stakes are real. Losing sight now is like pausing a documentary at the exact moment the wildlife finally steps into frame. But the story is not over. The same physics that hid our visitor will let it step out again as elongation grows. When it does, every photon we catch will either confirm that alien comets behave like ours or nudge us toward a stranger, wider view of how worlds are made. Before the comet slipped into the sun's glare, it left a trail of hints. Not smoking gunproof, not a single jaw-dropping image. A string of small tells that, together, sketched a nervous system on the edge, brightness that rose, stalled, then jumped, a coma that sometimes looked thinner than it should, a path through space that needed constant fine-tuning because tiny pushes kept nudging it off the perfect curve. Let us translate each clue. Comets usually brighten in a fairly smooth way as they fall toward the Sunday. More light, more warmth, more ice turning straight to gas, more dust lofted into space. 3i Atlas did not play that melody straight. The light curve flattened for stretches, then surged in little bursts. That pattern often points to sealed surfaces that crack open in episodes. Imagine a crust like scorched foam sitting atop cold ice. Most days it suppresses the flow. Then sunlight finds a seam, pressure pops a panel, and a jet roars for a while before choking again. The coma, that fuzz of gas and dust around the nucleus, is a truth teller. Thick coma usually means generous gas production. Thin coma can imply several different stories. The nucleus might be stingy with gas because there is more rock than ice, or the gas might be rich in volatiles like carbon monoxide that do not drag much dust with them, leaving the cloud faint in visible light. There is also the possibility of a surface blanketed by old dust that insulates the ice beneath. In that case, only a few vents feed the coma, and the overall cloud looks meager until new fractures form. Now, the orbit. In textbooks, orbits are smooth conic sections carved by gravity alone. Real comets cheat. Every jet is a tiny thruster. When a vent fires on one side of a spinning nucleus, it gives a gentle push that shifts the track. Astronomers call those shifts non-gravitational accelerations. They are small, but they accumulate. You can see them in the math when the best fit path drifts and the uncertainty around the next predicted position grows. For 3i Atlas, the fit kept asking for updates. That is a hint that jets were acting in irregular patterns, or that the object was not a neat, solid body at all. A few images added spice to the puzzle, elongated condensations, slight asymmetries. None clean enough to declare a split, but suggestive of strain. Fragmentation is a classic comet fate near the Sunday. Weak materials, thermal stress, spin up from jets, and tidal nudges can work together until cohesion fails. Sometimes a single large piece peels away, and you get a pair. Sometimes you get a train of small pieces that briefly make the whole system brighter, because fresh ice is suddenly exposed. Just before solar conjunction, 3i Atlas looked like it could be entering that arena. Could be, not must be. We also had hints in colour and spectrum. Some observers reported a relatively subdued dust signature, paired with signs that more volatile ices were active early. That picture fits an object with either a dust coating that muffles water vapour vents until closer to the sun, or a nucleus composition that leans colder. If carbon monoxide and carbon dioxide are doing more of the work far from the sun, you can get activity without the fluffy dust bloom that makes a comet photogenic. When that happens, the eye sees less even while the physics is busy. Spin states sat behind all of this like a metronome we could barely hear. The way brightness flickers as a comet rotates can reveal its day length and shape. If jets torque the body, that day length can change. Spin up is dangerous because rotational stress adds to thermal cracking. If the nucleus is already a contact binary, two lobes touching gently, torque can pry the lobes apart. In the final days before conjunction, the light curve hints were thin, but the need for frequent orbital refinements whispered that directional outgassing was not trivial. Put the clues together, and you get a range, not a verdict. On the cautious end, this is a dusty, somewhat insulated nucleus with a handful of active zones that turn on and off, creating the staircase pattern in brightness and the push-me-pull-me deviations in the path. On the dramatic end, this is a fragile pile beginning to split, with elongation in images marking the earliest stage of a break. Either way, the physics agrees on one thing. The stretch near the sun is crunch time, heat drives deeper, jets become erratic, stress lines lengthen. Here is the part that matters for what comes next. Those same clues shape our search plan when the comet re-emerges. If activity was patchy, it might return faint at first and brighten in pulses, so observers will sweep a wider mean anomaly window and accept a frustrating number of empty frames. If fragmentation began, recovery might show multiple condensations spread along the orbit rather than one neat core. That means photographers will need longer exposures and careful processing to tease out soft knots from the background. If the comet carried more rock than ice, it might come back looking like a star, with little to no coma, a fake asteroid in need of spectrum to prove its identity. Uncertainty is not a weakness here. It is fuel. Each ambiguous clue sharpens a testable prediction. If fresh ice panels were popping, we should see the color of the coma shift as different ices take turns. If jets were torquing the rotation, we should measure a changed day length. If early fragmentation truly began, the spacing of any returning pieces can tell us when the split occurred and how fast the parts drifted. The comet left us a handful of breadcrumbs. The next act is following them into daylight. Picture a comet not as a snowball but as a breathing worldlet. On the night side, it sleeps. On the day side, sunlight bores in, wakes ices, and jets begin to hiss. Around the nucleus, a cloud forms as gas escapes and drags dust with it. That cloud is the coma, and the coma is where the solar wind arrives like weather from another star. Plasma meets vapor, magnetism meets molecules. The encounter is far from gentle. Start with ionization. Sunlight and charged particles strip electrons from molecules streaming off the nucleus. Neutral gas becomes charged gas. The solar wind carries magnetic field lines frozen into its flow, and those lines drape around the comet like a cape. Where the wind first slams into the outflowing gas, a shock front forms. Downstream of that front, the magnetic field lines stretch and align, pulling a long, straight structure away from the sunday. That is the ion tail, the electric blue sword you see in deep images. It is not merely pretty. It is a live readout of what the wind is doing. Now add turbulence. The wind is not smooth. It gusts. It ripples. Magnetic orientation swings. When that happens, the ion tail can kink or even snap. Disconnection events are exactly what they sound like. The tail severs, a bright knot slides away downwind, and a new tail grows from the coma. Spacecraft have watched these amputations from up close, and Earth telescopes have caught them from afar. They are a reminder that comets wear the space weather on their sleeves. Dust plays a different game. Dust particles are heavy compared to molecules, and do not care much about magnetic fields. Sunlight pushes them with gentle pressure, and as they stream away, they carry a memory of the motion of the nucleus at release. That is why dust tails bow into graceful curves, while ion tails point almost straight away from the sunday. In photographs of active comets, the two tails can separate into distinct structures, one narrow and straight, one wide and arcing, a duet conducted by light and magnetism. Heat is the third actor, and near the sun, it upstages the rest. Thermal stress creeps into cracks. Each jet is also a recoil thruster, twisting the body over days and weeks. Spin rates change. If rotation quickens, the forces trying to tear the nucleus apart climb. A contact binary, with two lobes barely holding together, can be pried open by nothing more exotic than uneven sunlight and persistent outgassing. That is why comets have such a reputation for drama at closest approach. The physics is relentless, and the materials are weak. History gives us both ends of the spectrum. Comet Lovejoy, a daredevil that scraped inside a handful of Earth radii from the sun's surface, should have died by textbook logic. It did not. It burst through perihelion, trailing a spectacular tail, then gradually faded after shedding a great deal of mass. 2 years later, a different visitor named Ison approached on a path that held similar promise of brilliance and simply unraveled into dust. In one case, structure and size carried the day. In the other, heat and stress won. The lesson is humility. We know the forces at work, but each nucleus brings its own fragile architecture and hidden flaws. Where does a fast solar wind fit into this contest? A trans-equatorial hole can drive streams near 700 kilometers per second. That boost in speed means a stiffer magnetic drape and livelier ion tail dynamics. A strong wind can raise the odds of tail disconnections and can rearrange charged environments around the nucleus. It can also strip away plume material more efficiently, thinning parts of the coma. What it does not do is magically fortify or doom the nucleus by itself. The decisive battle still happens in the crust and the core, where heat diffuses, pores open, and cohesion either holds or fails. 3I, Atlas entered this arena during a loud solar episode. If it is dense and internally strong, it may use the wind as a canvas, painting a long, stable ion tail once it re-emerges while its core survives with scars. If it is porous and already cracked, the same conditions could make its charged envelope unstable and its jets more chaotic, tipping it toward a train of fragments. There is also the wild card of dormancy. Sometimes a crust sinters and seals, strangling venting until a later crack reawakens activity. In that scenario, the comet could come back looking quiet, then flare weeks later when sunlight finally breaches a seam. What should we watch for first? The color and shape of the tail tell you about the wind. A straight, narrow, bluish tail speaks of ions and strong magnetic guidance. A broad, pale fan suggests dust dominating the show. Rapid changes in the ion tail's direction or clean severings point to turbulent space weather. Brightness that pulses on daytime scales hints at rotating jets and uneven terrain. A subtly shifting spin period measured through light variations would be the smoking gun for torque from outgassing. Here is the part that makes this a shared experiment. Space weather monitors upstream of Earth will log wind speed, density, and magnetic orientation in near real time. Coronagraphs will sketch the glare near the Sunday. Ground images will sweep the predicted arc, each clear dawn and dusk. When a thin needle of ion glow first stabs out of the glare, we will know the wind is writing on the comet again. When or if a second point of light appears along the orbit, we will know the nucleus wrote back with a fracture. Plasma and ice are not natural enemies. They are partners in a performance that plays out every time a comet dives inward. The sun provides the orchestra, the nucleus provides the instrument. 3I Atlas is about to step back on stage. Whatever song it plays next, we will be ready to hear the physics in it. Start with the simplest path. Best case, 3I Atlas comes back looking like itself, only leaner. The coma swells, the tail forms, the light curve climbs along a steady arc. Spectra show water vapor, carbon compounds, the usual fingerprints of a sun-warmed traveler. The orbit solutions tighten as non-gravitational nudges settle into a pattern that our models can swallow. We breathe out, because this outcome means the nucleus carries enough strength and enough uniformity to survive a close brush with heat and wind. We learn that alien-made ice can be as tough as the local kind. We add a clean data set to the small library of interstellar visitors, and we move from fear to measurement. Now, flip to the stark end. Worst case, nothing returns. We point telescopes where the object should rise from glare, and the sky stays blank. Days pass, then weeks. A scatter of deep images yields only background galaxies and noise. The postscript writes itself. The nucleus disintegrated near closest approach, its pieces sanding themselves down to dust so fine that it spreads and thins into invisibility. That ending is not failure from a science point of view. It is a hard answer about structure and strength. It says some interstellar bodies are so porous, so fractured, or so volatile-rich that they cannot survive the inner system at all. It tells interception missions of the future to plan for fragile targets that can vanish when the stove gets hot. Between those poles lies the messy middle where comets love to live. A chain of small condensations could appear along the predicted path like droplets strung on a thread. That is the fragmentation family of outcomes. It begins when thermal stress opens existing cracks, jets spin the body faster, and a weak neck between lobes or layers gives way. In the hours or days around the break, fresh ice is exposed. Gas roars. The total brightness can spike because several surfaces sublimate at once. New pieces drift apart under tiny forces, and the train lengthens. For that outcome, The first clue will be a slight elongated blur, then 2 points, then 3, then a handful. Photographers will stack longer exposures and trace a delicate procession across the sky. Dormancy is another path. Heat can sinter the surface into a crust that throttles activity. The comet then masquerades as a dark rock, star-like in a small scope, easy to overlook. Weeks later, a seam opens, and a sudden flare announces that buried ice still has something to say. That path will test patience and change the cadence of observations. Watchers will need to keep returning even after the early frames disappoint. In return, they will catch the moment a sleeper wakes and learn how long crusts can bottle up energy. There is also a scenario that breaks prediction in a good way. Strangest case, the comet reappears not weaker but briefly stronger. A pre-existing fracture might have lifted a lid from a pocket of fresh volatile rich ice. Sunlight strikes, sublimation surges, the total reflective area jumps as gas drags out a wealth of dust. For a short window, days or a handful of weeks, 3I Atlas could punch above its weight, growing a dramatic ion tail and a broad dust fan. Viewers would see a genuine show, and modelers would take careful notes on how newly exposed layers change the chemistry of the coma. How do we tell these stories apart quickly and cleanly? The light curve is the heartbeat. Steady climb points to survival. A sawtooth pattern with sudden steps hints at cracking vents and patchy activity. A spike followed by a fade can mark fragmentation. Color matters too. A shift toward the blue end with a straight, needle-like tail favors ions and a strong wind. A whiter, wider fan favors dust and fresh surface exposure. The shape of the central condensation carries clues. A round, compact core suggests a single nucleus. An elongated core or a pair of peaks suggests splits. Repeat images on consecutive nights lock those impressions into facts. The orbit solution will also talk. If there is one body, and its non-gravitational terms stabilize, we are in the best case. If the solver keeps adding components or the residuals balloon, we are likely tracking more than one piece. The spacing between any fragments will let us rewind to estimate when the break began, and at what relative speed the pieces drift. Those numbers become a fingerprint of the stress regime that tore the comet open. Emotionally, it helps to decide in advance that all outcomes are wins for knowledge. The best case rewards patience with a clean baseline. The worst case teaches limits and forces humility. Fragmentation gives us a natural laboratory for how structure fails and how fresh layers change chemistry. Dormancy and surprise flares remind us that the surface is not a uniform blanket. It is patchwork, stitched by time and stress, ready to change with one crack. There is one more thread that runs through all of this: participation. These outcomes are not revealed by a single glamorous snapshot. They are stitched from sequences of ordinary images and small measurements taken by many eyes under many skies. That is why 1,000 backyards will matter as much as a handful of great domes. The first hint of a second point, the first measure of a changed period, the first color shift. They will not arrive in a press release. They will arrive as whispers that become a chorus. So choose your favorite path if you must. A survivor, a ghost, a string of beads, a sleeper who wakes. Then be ready to let the sky correct you. The beauty of a live investigation is that you do not have to pick a hero in advance. You only have to keep looking long enough to let the truth assemble itself out of light. Start with geometry you can feel. When an object sits too close to the sun in our sky, the glare drowns it. As days pass, the angle between the object and the sun grows. Astronomers call that angle solar elongation. Small angle means invisible. Bigger angle means hope. Late October into early November, that angle begins to open enough for careful searches. First from space, then from Earth. Space has the best tools for peering near the sunday. Coronagraphs create an artificial eclipse by placing a tiny disk in front of the blinding photosphere, letting fainter things just outside the hidden sun pop into view. The Solar and Heliospheric Observatory carries such eyes. So does the Solar Terrestrial Relations Observatory, with vantage points that do not match Earth exactly and sometimes catch what we miss. In those frames, 3I Atlas would not look dramatic at first. Think needle-thin tail forming before the head brightens. Think a moving fleck pinned against a sea of speckles. The earliest recovery could be nothing more than a consistent twitch at the correct place in consecutive images. As elongation grows past the low teens in degrees, specialized ground-based searches can join, starting at twilight when the sun is below the horizon, yet the comet is not. Wide-field cameras will scan along the predicted path, stacking short exposures to coax a faint smear out of a sky still bright with scattered sunlight. The first trick is to know where to look. Orbit models give a track and an uncertainty swath. The recent hints of non-gravitational pushes mean the swath is wider than we like. That is fine. You sweep. You listen for a whisper of motion. The schedule is not one night, then done. It is a ladder of windows. A few dawns at the end of October. A pause for weather. A deeper push in the first week of November as the angle improves. If recovery fails early, patience pays. Every day adds separation from the sun and subtracts glare. Every day also changes the story the comet tells. If it survived, activity can strengthen as surfaces settle and jets stabilize. If it broke apart, fragments spread and fade. So time is not your friend. What will a yes look like? In a coronagraph, the ion tail is often the first to betray a comet. A straight thread pointing away from the sun is easier to see than a small head against the messy background. On the ground, a point that moves from night to night is the signature. If there are 2 points in line with the track, the heart rate spikes. If there is a fuzzy core with a hint of elongation, you book a second night immediately and change nothing about your setup so the comparison is clean. Spectra come next. Even a small prism on a modest scope can separate light enough to see broad signatures. A bright green tint tells you diatomic carbon is singing. A blue cast in a straight tail tells you ions are dominating the show. Water bands are harder in small gear, but bigger instruments will chase them as soon as coordinates are solid. Chemistry confirms identity and reveals what changed during the blackout. The tools for the vigil are not only in national observatories. A backyard tracker, a low-noise camera, a careful logbook, and patience can contribute. Set up before the search window. Practice on a star field with a known asteroid so you can judge motion. Learn your horizon and where brightness gradients from city glow will make life difficult. Take many short exposures rather than one long one to beat the low-altitude blur, then stack in software that respects alignment on moving targets. Record the time for every frame with care. Small errors in time complicate orbits. While you watch, upstream monitors near the Earth-Sun line will be sampling the solar wind. Speed, density, magnetic orientation. Those numbers tell you what kind of ion tail behavior to expect. A steady orientation can make a needle tail that holds direction hour by hour. A twitchy field can yank the tail like a windsock in gusts. If the wind is strong and the comet weak, a clean tail disconnection is possible, a visible severing that leaves a glowing plug sliding downwind while a fresh tail grows. Expect false alarms. Noise spikes masquerade as needles. Hot pixels in a sensor pretend to be fragments in perfect straight lines. Clouds thin to a veil that looks like a coma. The antidote is repetition and careful control tests. Take an image, then dither the pointing slightly, and take another. Hot pixels stay put. Real things move. Ask a friend hundreds of kilometers away to repeat the sweep on the next clear night. Coincidence vanishes under parallax in time. If recovery succeeds, the tempo changes fast. Orbit solvers eat the new positions and spit out refined predictions. Exposure plans update. Spectrographs roll in. If a second point appears, teams begin measuring separations and relative brightness to back out when the split occurred and how much surface was freshly exposed. If nothing appears through the first good window, the message is not final. The door remains open while elongation grows. The vigil shifts from daily sweeps to deeper weekly passes that look beyond the first arc. This is the quiet thrill of live science. There is no dramatic countdown and no guarantee of fireworks. There is a community marking dates, sharing frames, and turning ambiguity into understanding. Somewhere out of the glare, 3i Atlas is either a survivor, a small procession, or a fading cloud. The only way to find out is to keep looking long enough for the sky to answer. While 3i Atlas hides in daylight, there is a comet you can point to with your own hands. Comet Lemon climbs the pre-dawn sky like a quiet lantern, bright enough for binoculars and under dark country skies flirting with naked eye visibility. If you have never seen a comet with your own eyes, this is your chance. The window is short. The next 2 weeks are the sweet spot, before glare and geometry make the hunt harder. Here is the plan. Set an alarm for 2 hours before sunrise. Step outside somewhere with an open eastern horizon. If you can see the faint river of the Milky Way on a good night, you are already winning. Face east and look above the place where the sun will rise. Lemon sits in the region of the sky, known as Cancer, drifting a little each morning. Naked eye, it may look like a soft star that refuses to focus. Through binoculars, it blossoms into a pale, fuzzy patch with a brighter core, sometimes showing a hint of a short tail if the air is steady. Binoculars beat a big telescope for your first look. 7 by 50 or 10 by 50 models concentrate enough light while keeping a wide field that makes finding the target simpler. Brace your elbows on a railing or rest the binoculars on a tripod to quiet the shakes. Sweep slowly. The human eye loves to skip past faint smudges on the first pass. Give each patch of sky a long count of 5. The comet will reveal itself with patience more than power. Your eyes are instruments. Treat them that way. Spend 10 minutes in darkness to let your night vision open fully. Turn off screens. Shield a single dim red light if you need to check a map. If you wear glasses, try both with and without. Some binoculars have enough focus range to compensate, and the extra glass can scatter light you are trying to catch. Above all, remember that comets are diffuse. A 4th magnitude comet can be harder to see than a 4th magnitude star because the same light is smeared over an area. Do not get discouraged if stars pop and the comet hides. Keep sweeping. What are you seeing in that faint fuzz? Sunlight is warming ices on the nucleus. Gas escapes and drags dust with it. The cloud around the core is the coma, and it glows by reflecting sunlight. A greenish tint sometimes peeks through because molecules called diatomic carbon fluoresce under sunlight. That green is a good sign that chemistry is working even when the tail is shy. Farther from the head, an ion tail may needle away from the sun, thin and bluish, while a dust fan curves gently. For lemon right now, expect modest structure. The beauty is in knowing you are watching a piece of the early solar system breathe. Why the 2-week rush? Geometry is your friend, and then your enemy. As the comet moves along its path, it climbs to a place where the angle from the sun is best for us before dawn. After that, the angle shrinks, and the sky brightens too quickly to give your eyes time. You have a run of mornings when everything lines up. Use them. Weather will steal some. Fatigue will tempt you back to bed. One clear morning is worth 10 cloudy nights of planning. If you want to bring back proof, your phone can help. Mount it to the binocular eyepiece with a simple adapter and record short video clips. Later, stack frames in software that aligns the stars. The comet will stand out better than in any single shot. If you have a small tracking mount, set it to sidereal rate and take a series of 10-second exposures with a fast lens. Between frames, do not touch the focus. The steadier your setup, the cleaner the stack. Keep a simple log, date, time, location, sky conditions, and a one-line description of what you saw. If you note how far the comet sits from a nearby bright star each morning, you will feel the sky move in your bones. That is more than romance. It trains your intuition for spotting faint motion when 3-Eye Atlas returns. The same habits that let you find lemon will let you find whatever slips out of the sun's glare later. Expect personality from night to night. Comets are living weather reports. Lemon's brightness may climb and stall in small steps as new vents open or seal. Hints of a short tail can lengthen or vanish with a change in the solar wind. Thin clouds can mimic a glow. City light can erase the comet completely even when stars remain. If you can, drive an hour into darker country. The difference between a suburban sky and a rural sky is the difference between frustration and joy. Most of all, let the scale land. That soft patch in your binoculars holds ice older than Earth, dust older than the mountains near you, organics that have been locked away since the sun was an infant. It has drifted for billions of years. For a handful of mornings, it rises on your horizon, asks you to make coffee in the dark, and rewards you with a small green breath in a cold sky. While we wait for an interstellar traveler to reappear, this is the comet you can actually greet. Start with a quiet driveway under a modest sky. A tripod, a small mount humming, a camera the size of your hand. That is the beginning of a global instrument made of ordinary people. Professional telescopes see deeper, but they are scheduled, oversubscribed, and weathered by the same clouds. The backyard fills the gaps. It turns a handful of nights into continuous coverage. It converts 1,000 small chances into a steady stream of discovery. Comets are perfect targets for this kind of networked patience. They brighten and fade on human timescales. Jets switch on in hours. Fragments separate by arc-seconds over a few nights. Those changes are too jumpy for weekly snapshots. They need eyes tonight and tomorrow and the next day, from different longitudes that can hand the baton across the planet as Earth turns. That baton pass is where you come in. You do not need exotic gear to matter. A mount that can track the stars smoothly, a short to medium focal length lens or a small refractor, a camera that keeps noise low and records clean, time-stamped frames. What you add that no national facility can replicate is attention. You can be ready the moment clouds part. You can pivot to a new target when a rumor becomes a signal. You can choose to keep watch on a patch of sky that would otherwise go dark. Here is how amateurs turn curiosity into data. First, fieldcraft. Learn the quiet mechanics that beat the sky. Polar align well enough that the stars do not smear in 10-second exposures. Focus until a bright star shrinks to the tiniest point your optics can deliver. Take many short frames instead of a few long ones to outrun wind gusts and poor seeing. Calibrate with darks and flats so your sensor's quirks do not founds. Masquerade as celestial structure. Then stack those frames carefully, aligning on the moving comet when you want the tail and coma to stand still, and on the stars when you want motion to reveal itself as a trail. Second, measurement. Photometry sounds intimidating, but the heart of it is comparing the comet's brightness to nearby stars of known brightness. Software can help, but the discipline is simple. Use the same aperture settings from night to night. Record air mass and sky conditions. Avoid saturating the comet's core. With consistency, your backyard light curve becomes a meaningful trace of the comet's heartbeat. If many observers do this with the same care, those traces weave into a robust story of rises, stalls, and outbursts. Third, astrometry. Position is power. When recovery begins, orbit solvers feast on precise coordinates from as many sites as possible. That is where careful timestamps and accurate plate solving matter. A single, well-measured point from a small scope can tighten the uncertainty corridor for the next night's search. When fragments appear, your measurements of their separations and angles help rewind the breakup to its birth hour. This is how ordinary pixels prune chaos into a path. False alarms will happen. Hot pixels pretend to be companions. Airplanes imitate streaks. Processing can create halos that look like comae. The cure is repeatability and community. Re-image the field with a small dither. If the candidate stays fixed relative to the sensor, it is noise. If it shifts with the stars, it is real. Share frames and logs with observers a few time zones away. If they see the same thing at a different hour under different air, confidence climbs quickly. The emotional engine here is ownership. When you catch a subtle brightening before the big scopes turn, you feel the thrill that built astronomy in the first place. When your measurement tightens a prediction others rely on, you become a link in a chain that runs from roof decks to research papers. That feeling is not a sentimental extra. It is the fuel that keeps people outside at 4 a.m. with cold fingers and warm coffee while the rest of the world sleeps. This is also an equity story. Not everyone lives near a major observatory. Not everyone can afford heavy equipment, but the price of a capable tracker and camera has fallen to the level of a used bicycle. Knowledge is the multiplier. Communities online teach each other good habits and quiet tricks. A rural school with a donated mount can contribute as surely as a seasoned hobbyist with a backyard peer. The sky does not care about your resume. When 3i Atlas steps out of the sun's glare, it will not announce itself with a drum roll. It will be a faint arrow of ion light, or an off-round point that shifts just enough between frames to make you lean forward. If a second point appears, amateurs will see it first. If the ion tail snaps and regrows, amateurs will stitch the sequence into a time-lapse the world watches. If the comet refuses to return, amateurs will be the ones who prove absence with night after night of honest negatives. The night belongs to anyone willing to look up and keep records. That is the quiet revolution of the backyard. It turns wonder into evidence and spectators into collaborators. The next chapter of this story will be written by many hands under many skies. If you have ever wanted to feel the gears of the cosmos turn and know that your fingertips were on the wrench, this is your invitation. Here is a question that will keep your group chat buzzing. What if comets are not driven mainly by sunlight and boiling ice, but by electricity? The so-called electric comet idea claims that as a comet plows through the solar wind, it charges up, currents surge, and electrical forces rip material from the surface, even causing explosive outbursts. It is a bold picture. It is also a minority one, so let us lay it out clearly, then test it in daylight. First, the claim in its best clothes. Space is a plasma. Plasmas carry currents and magnetic fields. A dark, dusty nucleus moving through that plasma should develop a potential difference, like rubbing a balloon on your sweater. At certain thresholds, the story goes, electric discharges crackle across the surface. Tail disconnections become sparks, not mere magnetic kinks. Brightenings become arcs, not vents. In this framing, chemistry and heat are side characters. The real driver is voltage, now the mainstream model. Sunlight strikes a cold, porous mixture of ice and dust. Ices sublimate, which means they go straight from solid to gas. That gas escapes through pores and cracks, entrains dust, and forms a flowing coma. Ultraviolet light and high-energy particles ionize some of that gas, so it becomes electrically active downstream. The solar wind's magnetic field drapes around this outflow. That interaction sculpts an ion tail that can kink, wave, and disconnect when the field shifts. The nucleus does not need to be a battery to explain any of this. It only needs sunlight, weak gravity, and fragile structure. Which story fits the measurements better? Start with energy budgets. Sublimation provides enormous latent heat, quiet, calculable power that becomes gas flow. We can measure the mass of gas leaving a comet from its spectral lines and show that the mechanical work done by those flows easily accounts for observed jet speeds and non-gravitational pushes on the orbit. If electricity were the prime mover, we would expect currents and fields of a particular strength near the nucleus. Spacecraft have flown through comet comae with magnetometers and particle detectors. They see the draped field, pick up ions and shocks predicted by the outgassing model. They do not see the kind of rapid, nucleus-scale discharges that the electric picture would require. Look at tail disconnection events. In the electric framing, they are sparks. In the plasma, with outgassing framing, they are what happens when the interplanetary magnetic field flips orientation or a compression region slides past, snapping the drape and forcing the tail to regrow. We can often time these breaks to solar wind changes recorded by upstream spacecraft. The alignment is not perfect every time space weather is messy, but it is good enough that you can call the play as the wind rotates. That predictive power matters. What about sudden brightenings? The electric comet narrative reaches for arcing. The thermophysical model reaches for pockets of volatile ice or structural failure that exposes fresh material. When comets break, the total area of sublimating surface can jump. That produces both more gas and more dust, exactly what images and spectra report. Laboratory work backs this up. Heat-porous ice dust mix and fractures propagate. Volatile rich pockets vent in rapid spurts. No lightning required. To be fair, there are electrical processes inside the mainstream model. The coma becomes a partially ionized gas, currents flow, fields wrap. Those dynamics shape the ion tail spectacularly, but they are consequences of outgassing and solar wind interaction, not the engine that powers the coma in the first place. That distinction is not pedantry. It is the difference between a house fire and the smoke. One causes the other, not the other way around. So why do electric models persist? Partly because they offer vivid images. Lightning is dramatic. Sparks feel intuitive in a way that sublimation physics does not. Partly because every big mystery attracts alternative frameworks that promise a simpler key. And partly because sometimes the mainstream gets details wrong or communicates poorly, leaving room for stories that feel more alive than a plot full of equations. The antidote is not mockery, it is prediction. An alternative must do more than sound exciting. It must put numbers on the table that a rival model cannot match, then survive. Contact with measurement. For comets, that means predicting tail behavior from solar wind orientation in advance. It means matching the observed gas production rates, jet speeds, and non-gravitational orbit changes without borrowing sublimation's energy. It means explaining the chemical fingerprints we see in spectra and the layering we find when spacecraft image crater walls in detail. Here is the humility piece. Fringe ideas sometimes push mainstream science to sharpen its tests. When a claim sprints ahead, it forces better measurements and clearer public explanations. If there is a small, overlooked electrical effect near nuclei, a good experiment will catch it. If not, the exercise still leaves us with maps that are more precise than before. So as we wait for 3i Atlas to reappear, keep two mental folders open. In one, the well-tested story of sunlight, sublimation, jets, and magnetic draping. In the other, any quantitative alternative that risks real predictions. When images arrive, we will file them where they fit best. The comet does not care which camp we favor. It will write its answer in light either way. The mind loves a tidy story. The sun roars, a comet vanishes, earthquakes follow, and the plot locks into place. Cause meets effect. Villain meets motive. We feel safer when events line up into a chain. The problem is that nature prefers webs over chains. In webs, many lines cross without touching. Coincidence becomes common simply because there are so many moving parts. Pattern hunger is not a flaw. It kept our ancestors alive. In tall grass, mistaking wind for a predator is cheap. Missing a predator is not. Evolution tuned us to connect dots fast and prune later. In modern science, that tuning needs a leash. The leash's math and method, base rates, controls, pre-registered questions that do not shift as soon as the result looks messy. Without the leash, the loudest pattern wins even when it is a cloud shaped like a tiger. Conspiracy. Stories step into the gap between what happened and what we can prove. They offer an almost irresistible trade. Certainty without the weight. Meaning without error bars. A shadowy actor turns chaos into plan, and fear relaxes because at least someone is driving. That psychological relief is real, which is why debunking with mockery backfires. The better move is to ask a handful of calm questions that any honest claim should face. Start with who could know. Big space missions and seismic networks involve thousands of people across agencies and countries. A secret that large leaks through ordinary human life. Paychecks, vendors, spouses, academia. If a story requires perfect silence from a cast that large across years, it is a fantasy about people, not a theory about physics. If it requires only a few people to miss a simple detail, that is plausible. Distinguish massive hidden coordination from everyday error. Next, ask what would change the number. Real science welcomes risk. It says here is our prediction, and here is the measurement that would disprove it. Conspiracy stories often shift goalposts. When one date passes without the promised reveal, a new date appears. When one image fails to show the hidden craft, the craft becomes invisible by design. Demanding a clear off-ramp protects your time and attention. If nothing imaginable could falsify the claim, it is not a claim about the world. It is a story about belief. Then check the clock. Did the explanation arrive after the fact? Tailored to fit the known twists. That is backfilling. Strong theories buy their groceries with advanced predictions. Weak ones shop on store credit, grabbing whatever fits the appetite of the day. For our night of the solar wind, the vanishing comet, and the earthquakes, a sober clock says the solar stream was forecast in advance, the conjunction geometry was known in advance, and earthquakes happen at a steady global clip. A map that puts the three together feels cinematic. The calendar says it was bound to happen sometimes. Opacity fuels suspicion. Space agencies release processed images because raw frames are ugly and need calibration. That can look like editing to hide the truth to anyone outside the room. The fix is sunlight. Publish processing steps. Share raw data when possible. Invite outsiders to run the pipeline. When the doors are open, the story of how we know becomes as interesting as what we know. In the long run, that starves conspiracy oxygen without turning off curiosity. There is also a language trap. Jargon is a fence that keeps nuance in and people out. When scientists say there is no evidence for a link, many hear there is no link. What the scientist meant is we tested and found nothing above noise with the methods we used so far. A better sentence is longer but kinder. We do not see a reliable signal yet, and here is how strong the signal would need to be for our instruments to catch it. That translation invites the public onto the team instead of onto the opposing bench. Here is a pocket toolkit you can keep without a degree. Ask how many similar days passed without the same pattern. Ask whether the claim is anchored to numbers you can check, like angles on a sky map or wind speed readings posted in public. Ask if the loudest version of the theory risked a prediction before the event. Ask what evidence would make the theorist change their mind, and whether they can answer that without flinching. If these checks feel boring, good. Boring is the point. Boring saves you from cliff dives dressed as revelations. None of this means turning down wonder. Wonder is the fuel. It means marrying wonder to patience so that surprise becomes discovery instead of detour. The sun will open more magnetic gates. More comets will skim the furnace. The ground will shudder again somewhere. Sometimes headlines will stack in unnerving ways. When they do, you can feel the thrill and still keep your hand on the brake. The cosmos is strange. Enough on its own. We do not need to invent shadows to make it dramatic. If a hidden link exists between sky and stone, it will leave a fingerprint that survives repetition and independent checks. If not, coincidence will remain what it always is, the noise floor of a busy universe. Either way, the work is the same. Watch closely. Write it down. Test what you think you saw. Then test it again. That is how a story becomes a result, and how a haunting pattern becomes a chart you can trust. Imagine sending a secret that tattles the instant anyone tries to read it. That is the promise behind quantum key distribution, the heartbeat of a new communications spine that China says now spans nearly 13,000 kilometers by chaining satellites and ground stations. The physics sounds like science fiction. It is also brutally practical once you unpack it. Start with photons, tiny packets of light that can carry information in delicate quantum states. Those states are like soap bubbles. Touch them, and they pop. The no cloning rule in quantum mechanics says you cannot copy an unknown quantum state without changing it. That rule turns eavesdroppers from invisible ghosts into elephants in a glass shop. If someone taps the line and measures the photons, they disturb them. The disturbance shows up as extra error in the key that two honest parties are trying to share. See too much error, throw the key away, try again on a fresh pass. There are two main flavors here. Prepare and measure, where a transmitter sends single photons in random polarizations and a receiver measures them in randomly chosen bases. Then both sides compare notes over a public channel to harvest the bits that survived cleanly. And entanglement distribution, where a satellite creates pairs of linked photons and sends one to each ground station. Measure one, and you learn something about the other instantly, even across long distances. The instant part does not carry messages faster than light. It does let two distant stations harvest identical random strings that become encryption keys without shipping those strings through a vulnerable channel. Put this on orbit, and the architecture looks like a relay race. A low-Earth satellite sweeps over a ground station, shares a quantum key, then later shares with a different station. Those links plus classical cryptography let distant cities share keys that never rode a conventional fiber in the clear. As more satellites and ground stations join, the hops chain together into an intercity web. China's claim is that this web now connects government and financial nodes across a continent-scale footprint with routine sessions, not just demos. Why does this matter now? Because the computers of tomorrow threaten the locks of today. Classical encryption relies on math problems that are hard for ordinary machines to solve within a useful lifetime. Quantum computers, if they reach large enough scale, could make short work of some of those problems. Adversaries can record traffic today and unlock it tomorrow when the tools mature. That is the harvest now, decrypt later threat. Quantum key distribution dodges it by moving security out of math and into physics. To steal the key, you must touch the photons. To touch the photons, you must leave a bruise. There are limits. Quantum channels are slow compared to classical ones. Measured in bits per second, key rates are a trickle next to the torrents that carry video streams and backups. That is fine. You do not send the movie through the quantum pipe. You send the padlock through the quantum pipe, and the movie through a normal line, now protected by a key you know was clean when it was born. Weather can also slam the window shut, because clouds scatter and absorb the dim light levels quantum channels use. Networks get around that by scheduling passes and hopping through clear skies when and where they can. There is also the soft underbelly called endpoints. Quantum methods can guarantee that the key arriving at a ground station is untampered. They do not guarantee that the computer that uses that key is honest or secure. Malware does not care about entanglement. A side channel that listens to power draw or electromagnetic leaks can whisper the secret out after the physics did its job perfectly. This is the unglamorous truth of security. The lock on the door can be flawless while the window is still open. The geopolitics follows quickly. A nation that runs a reliable quantum backbone gains confidence that its most sensitive signals will remain safe for decades, even against future computers. That is an intelligence advantage and a negotiating chip. It can change how states think about deterrence and coercion in the information realm. It can also create pressure for standards. Whose satellites do you trust? Whose detectors? Whose calibrations? A global network without shared rules looks like a patchwork of gated communities and suspicious neighbors. Skeptics ask a fair question. Are the links truly quantum end-to-end, or do they rely on trusted intermediate nodes that could be compromised? Early networks used relay stations where keys were decrypted and re-encrypted locally, creating a point of failure if you did not trust the operator. The goal now is to stitch together paths that keep the key material quantum as far as possible, or to confine trust to hardware that can be audited and sealed. Future devices called quantum repeaters may extend the reach of pure entanglement hops across continents without those classical pit stops, but they are not ready to leave the lab yet. There is a surveillance paradox hidden in all of this. Quantum channels can protect the content of messages. They do not hide the fact that two parties are talking. Metadata still blooms. Who contacted whom, when, and how often? That pattern can be as revealing as the words themselves in the hands of a powerful state. A nationwide quantum network could thus be both a shield and a spotlight. It can keep adversaries out and keep citizens on a leash. Technology does not choose. People do. Pull back, and the rhyme with our comet story appears. We are chasing messengers in hostile environments. For comets, chemistry has to survive sunlight and wind to reach our telescopes. For us, Fragile quantum states have to cross air and space to reach a detector without collapsing. Both teach the same lesson. Information is physical. To move it safely, you have to respect the medium, map the noise, and plan for thieves. If the claims hold, a continent-scale quantum whisper network is now a working piece of 21st century infrastructure. Expect others to build their own. Expect alliances to negotiate shared nodes with careful eyes on trust. Expect endpoint hacks to grow bolder as the pipes themselves harden. And expect a race not only for bigger computers but for better detectors, cleaner sources, faster pointing, and smarter scheduling. The future of secrecy is not only math on a whiteboard. It is photon by photon engineering under real skies. Picture a lab that smells faintly of bread dough. Not bleach, not solvents. Yeast are working, but this is not beer. Inside those tanks, engineered microbes are taking something we throw away every day and coaxing it into the mineral that makes your bones hard. Waste becomes structure. It sounds like a prank until you follow the chemistry step by step and watch crystals grow. Start with the waste stream. Human bodies are amazing at turning food into motion, thought, and warmth, but there is leftover nitrogen that must exit. We ship it out in urine, mostly as urea dissolved in water. Cities collect it, mix it with everything else in sewage, and spend energy to strip nitrogen back out because too much in rivers sparks algal blooms and dead zones. That is the old loop. The new loop asks a different question. Instead of paying to throw nitrogen away, could we harvest it as feedstock for something valuable? Enter hydroxyapatite, the major mineral in bone and teeth. Think of it as a calcium phosphate lattice, a crystal that is hard yet friendly to living tissue. Surgeons love it for bone grafts and dental implants because the body recognizes it, grows into it, and anchors to it. Industry can make hydroxyapatite with heat and chemicals. Nature makes it at body temperature, one dissolved ion at a time. Synthetic biology tries to meet nature halfway, asking microbes to run the steps gently in water instead of in a furnace. How does a yeast cell help? Engineers add genes that give the yeast a new set of tools. One breaks down urea into components the cell can use. Others nudge the internal chemistry toward producing the right balance of calcium and phosphate ions in the broth around the cells. Under the right pH and temperature, tiny crystals of hydroxyapatite start to nucleate and grow. The yeast are not becoming bone. They are creating a chemical microclimate where bone mineral forms and falls out of solution as a fine powder that can be filtered and refined. The first question you should ask is purity. If the goal is medical-grade material inside a human body, you cannot tolerate leftover proteins, endotoxins, or random ions riding along. Early lab results show that with careful control, the crystals can match the shape and structure of natural bone mineral. That is promising, but turning a beaker win into a clinical product is a long road. Every step must be clean and repeatable. Every contaminant must be below strict thresholds. That is not a reason to scoff. It is a reason to invest in better purification trains and smarter bioreactors. Yield is the second worry. A few milligrams per litre is a curiosity. Kilograms per day are useful. The current methods are not ready to flood the market, but the knobs are obvious. Strain tuning, growth conditions, reactor design, and downstream processing all have room to climb. Think of where brewing stood when people first selected hardy yeasts for better flavour and faster fermentation. Scaling biology is slow until it is fast, and then it becomes routine. Beyond the clinic, there is a simple ecological win. Every gram of nitrogen you pull from urine and lock into a solid is a gram you did not send to rivers. Instead of diluting a problem across a watershed, you concentrate it into a bag of useful powder. Cities that separate urine from other wastewater at the source could, in theory, pipe that stream to small plants that run quietly, making a saleable material while easing the burden on treatment facilities. It is not glamorous. It is exactly the kind of infrastructure fix that adds up when millions of people flush every day. Then there is space. A habitat on the Moon or Mars must be a circular economy with walls. Every atom that goes out must go somewhere planned. Urine will already be captured for water recovery. Divert some to a bioreactor, and now you have a stockpile of bone-friendly mineral for medical emergencies, or for coatings that help implants bond if someone breaks a limb far from Earth. Waste becomes safety. That is the kind of redundancy mission planners crave. Culture is the friction here. Even when chemistry erases origin, people remember stories. The idea of a bone graft bone powder born from urine may trigger disgust. There is a path through that resistance. Transparency about purification, independent testing, clear labels about performance, not provenance. In the hospital, atoms are atoms. The choice should be about what heals faster, integrates better, and lowers risk, not about where the calcium took its last bath. There is also a justice angle. Synthetic hydroxyapatite, made in giant kilns, costs money and energy. If microbial production at room temperature can reduce energy demand and lower price while maintaining quality, more patients in low-resource settings could receive grafts that speed recovery. An idea that began as a clever lab trick becomes a lever for wider access to care. Do not romanticize the road. Lab bench success does not guarantee factory floor stability. Regulators will rightly ask hard questions and demand data that takes years to gather. Some companies will hype and then ghost when margins refuse to appear, but the direction is sound. Biology is very good at moving atoms gently into intricate shapes. Teaching it to move waste atoms into useful shapes is both an environmental bet and a medical one. Zoom out, and the rhyme with our larger story becomes clear. The universe runs on cycles. In comets, ancient ices sublimate and fall back. In cities, nutrients can loop or leak. In labs, we can choose to design for return rather than discard. Turning urine into bone mineral is a small, almost mischievous example of a serious principle. Close the loop, and strange becomes normal. In a decade, the idea that we ever mined mountains for calcium while flushing nitrogen into rivers may sound as odd as it feels today to grow bone powder from yeast and waste. Try not to yawn while you hear this. A small striped fish in a lab tank watches a neighbor yawn, and then yawns too. That should not be possible if contagious yawning demands the social machinery we usually attribute to big-brained mammals. So, either our requirement was wrong, or evolution built similar tricks with very different parts. Start with the setup. Zebrafish live in adjacent clear tanks. Cameras roll. Researchers nudge one fish toward yawning the old-fashioned way, lowering dissolved oxygen for a short, safe window that makes gill and jaw movements stretch wide and slow. Across the pane, the observer fish swims normally. Then, within seconds to minutes of the model fish's exaggerated gape, the observer's jaw yawns more often than baseline, and more often than in control trials where nothing is happening next door. That timing correlation is the spark. It suggests social contagion rather than coincidence. Here is why that is weird. In humans and other social mammals, contagious yawning has been linked loosely to empathy circuits and to mirror neuron systems, networks that fire both when you act and when you watch someone else act. Fish do not have a folded cortex like ours. Their brains are organized differently, smaller and simpler by our standards. If they still yawn contagiously, then either yawning does not need the cortical machinery we assumed, or fish have converged on a different neural route to the same behavior. Before we crown a new champion of empathy, we have to clear some hurdles. First, are we sure the fish are yawning, and not just flexing jaws for another reason? The movement pattern looks like classic yawns: wide gape, slow stretch, brief pause, slow close. It increases under mild oxygen dips and under stress, as it does in other species. That is reassuring. Still, replication under tighter control is key. Second, could shared environmental cues be fooling us? If pumps, lighting, or subtle vibrations in one tank change during the model fish's yawn trigger, the observer might be responding to the same cue, not to the sight of the neighbor. Good designs eliminate those leaks by isolating water systems and synchronizing the lab environment across tanks. Assume the effect holds under those stricter tests. What does it mean? One path says yawning contagion is an ancient, low-level coordination reflex. A visual cue, a conspecific's massive gape, ticks a simple sensory motor link that spreads state changes through a school. In that picture, you do not need empathy as humans mean it. You need a detector, a trigger threshold, and a motor program ready to fire. Another path says, fish's social brains, yes, they have them carry richer maps than we credit, capable of mapping others' actions onto their own bodies in a primitive but real form of mirroring. Either way, the function might be practical. Schools move as one by following simple local rules. Keep distance, align, turn when your neighbor turns. If yawning tracks arousal or oxygen demand, spreading that signal through a group could synchronize readiness rest to alert, or oxygen debt to oxygen balancing so that the school transitions together. Social species crave coordination. Yawning could be one of the subtle switches that set a group's tempo. Now, why do we care beyond fish trivia? Because every time an unexpected species passes a supposedly human-flavored test, we have to renovate our map of minds. Tool use is not only for primates. Culture is not only for people. Navigation with cognitive maps is not only for mammals. A contagious yawn in a fish tells us either that complex behaviors can be assembled from simpler parts more often than we thought, or that evolution reuses motifs across huge distances on the tree of life. Both conclusions nudge us toward humility. There is also a methods lesson. When we talk about mirror neurons and empathy, we risk turning rich but fuzzy ideas into magical labels. The cure is precise hypotheses and risky predictions. If fish yawning is truly visually contagious, then blocking sight should crush the effect, while smell or pressure cues alone should not rescue it. If it reflects stress coupling, then hormone levels should rise in observers who yawn more. If it coordinates oxygen behavior, then group yawning should correlate with changes in gill ventilation and fin stroke patterns that stabilize school spacing. Those are testable. Those make the story tight. Do not miss the human echo. We yawn when others yawn, more when we are tired, more when we are bonded. We also project our minds into animal faces too easily. The way out of projection is not to deny minds to other creatures. It is to measure with care. Fish have different bodies, different senses, and different worlds. If they still show a form of social contagion, we should expand our definitions, not shrink theirs to fit our comfort. Hold the paradox in your head. A tiny fish that can be raised by the hundreds in a classroom tank might be teaching us about the roots of social resonance that ripple through flocks, herds, and crowds, including human crowds at a concert or a stadium. The same physics of coupled oscillators that makes fireflies sync their flashes and planets lock in orbital ratios might also whisper through brains, nudging rhythms toward alignment when a neighbor yawns. The next time you catch a yawn you did not start, remember a striped fish in a quiet lab and smile at how wide the family of minds might be. Mark the calendar now. On an April evening in 2029, a space rock roughly the size of a city stadium will sweep past Earth closer than many satellites. You will be able to step outside, look up, and watch a new star crawl against the constellations with your naked eyes. That has never happened in recorded history for an object this large. It is not a movie trailer. It is orbital mechanics keeping an appointment. Meet Apophis, number 99,942 in the catalogue, but first in our hearts for pure drama. Early calculations after its discovery in 2004 flirted with impact odds that raised pulses. As more data arrived, the uncertainty shrank and the doomsday headlines evaporated. By now, the 2029 pass is ruled safe. That is the first truth to keep in your pocket. Safe does not mean boring. Think of Earth's gravity as a hand you wave near a passing leaf. The leaf's path bends. Apophis will feel that bend. The flyby will deflect its orbit around the sun measurably, changing its year length and future appointments. The exact amount depends on the geometry of the pass, which depends in turn on details we will pin down by tracking it obsessively throughout the encounter. Measure before, measure during, measure after. The arc becomes a clean experiment in celestial billiards. Radar is our superpower here. When the asteroid is close enough, giant. Dishes ping it with radio waves and listen for the echo. The time delay gives distance to meter precision. The Doppler shift gives speed to millimeter per second precision. Stitch those together, and you can build images that reveal shape and spin, craters and boulders, ridges and hollows. If you loved the potato shapes of past near-Earth asteroids, prepare for a crisp, rotating model of Apophis, sculpted by math and echo. Spin matters because sunlight does more than warm rock. It pushes. The Yarkovsky effect thermal photons leaving a warm afternoon side acts like a tiny thruster that can, over years, move an asteroid kilometers off a naive path. The close flyby gives us leverage to measure that push precisely by comparing reality to predictions with and without thermal recoil. Once calibrated, we can forecast later encounters confidently and squash fresh waves of rumor before they crest. Tides add spice. The same differential pull that raises bulges in Earth's oceans will tug on Apophis. If it is a rubble pile, a loose heap bound by weak gravity, Earth's pull could rearrange its surface, trigger small landslides, or even tweak its spin rate. We saw hints of that kind of reshaping after other close passes for smaller objects. Apophis gives us a front row seat to watch geology without atmosphere, weather, or water, just gravity and grit arguing in slow motion. Public risk communication will be a test. The words 1 in 45,000 sound different to a statistician than to a parent packing lunches. The fix is pictures and context. Show the track, the error ellipse, and how it shrinks as more observations land. Show how radar slices the uncertainty, like a chef with a sharp knife. Show how the deflected path after 2029 misses key gravitational keyholes that could have set up future hits. Confidence is not magic, it is measurement plus math, told clearly. The flyby is a gift to planetary defense. NASA's DART mission proved we can shove a small asteroid slightly by hitting it with a kinetic impactor. Apophis is bigger and passing closer. A rendezvous mission, if approved, could ride along, mapping the surface at meter scale, sniffing composition, and dropping reflective markers so ground radar can track rotation changes with ridiculous precision. It could even test a gravity tractor concept by flying in formation and letting its tiny pull tug the rock's path by a measurable hair. Every technique we learn on a friendly flyby becomes a tool for a not-so-friendly future. Your role that night is simple and kind of wonderful. Go outside 30 to 60 minutes after sunset, find a decent dark patch of sky away from street lamps, and look for a point of light moving faster than a satellite and slower than a meteor. Binoculars make the crawl obvious. A tripod and a camera can capture a time-lapse trail bending through the starfield. If you have never felt orbital mechanics in your bones, watching a mountain drift between you and the distant stars will do it. Expect a wave of nonsense too. Claims of tidal disasters, atmosphere stripping, and secret NASA panic will flare and fade. The moon and sun tug Earth's tides orders of magnitude more than Apophis can. The air will not flutter. The birds will keep singing. The only widespread effect will be a rise in backyard enthusiasm and maybe a few traffic jams at dark overlooks. Let the teachable moment breathe. It is rare for orbital dynamics to hold a primetime slot. There is a deeper reason to care. Civilization is finally building the detection nets, the tracking pipelines, and the playbooks that add up to cosmic insurance. We find things early. We model their paths with honesty about uncertainty. We practice deflection on targets that do not scare us. We keep the public looped in so that trust grows instead of rotting. Apophis is a midterm exam in that course. If we ace it, the final, whenever it comes, will be less terrifying. In a century of grim headlines, here is one that can unite. People on every continent will look up at the same moving point. For once, not a satellite we built, but a natural visitor, reminding us that we live in a dynamic, flying graveyard of leftover planet parts. We have the brains, the math, and the tools to not just watch, but to act when it matters. Watch Apophis, cheer the radar teams, show a kid the crawl. This is what a confident species looks like when it faces the sky. Circle a night in late September 2040, step outside after sunset, and the sky will feel busier than usual. Mercury, Venus, Mars, Jupiter, Saturn, and, with binoculars, Uranus will all cluster within a generous slice of the ecliptic. Not a single file line, not doomsday geometry, just a rare, photogenic chord in the grand music of orbital periods. Let us name what this is and what it is not. It is a planetary parade, several bright worlds sharing the same region of sky for hours. It is not a literal alignment in space. The planets will be spread across tens to hundreds of millions of kilometers, merely projected into our line of sight. That distinction matters because it kills the old myth about gravity piling up to yank tides or trigger quakes. The moon and sun dominate Earth's tides by a comical margin. Planets, even bunched, are background dancers in that department. So why does a parade feel special? Because it compresses timescales into something your senses can digest. Mercury whips around the sun in 88 days, Venus in 225, Mars takes almost 2 Earth years, Jupiter 11 plus, Saturn 29. Their different tempos almost never give us the gift of many bright dots in one patch of sky at once. When they do, you feel the clockwork. You can literally watch Mercury slide night by night, see Venus blaze like a lighthouse, and catch Mars's orange ember drifting near the glitter of Jupiter's retinue. Here is how to get most from it. Give your eyes an hour after sunset to drink in the dark. Start with Venus, brilliant, unmistakable, then drop inward toward the glow, for Mercury hugging the horizon. Mars will sit higher, warm and small, while Jupiter dominates with a steady, cream-coloured light that does not twinkle as much as stars around it. Aim binoculars at Jupiter and the Galilean moons click into view, tiny points in a line. Slide to Saturn, and even in modest optics, the ringed disk resolves into a toy model that still knocks the wind out of you. Uranus will be the shy one, a pale dot that needs a finder chart and a steady hand. If you have a camera, you can tell a story the eye alone cannot. Use a wide, fast lens on a tripod and take a series of 10-second exposures at high sensitivity. Each night, frame the same foreground, a skyline, a a tree, a ridgeline, and let the planets crawl right itself over weeks. Later, align the shots and build a time-lapse where points weave and trade places. The dance is slow in human moments, fast in the language of months. Watching it play back reminds you that orbits are motion, not static charts. The science payoff here is not gravitational fireworks. It is calibration and comparison. With several bright planets in range during the same observing window, instruments on the ground can sweep spectra of their atmospheres in similar conditions, same temperature, same humidity, same instrument state. That cleans the data. Amateurs can join in by making simultaneous color measurements, building a citizen science palette of planetary hues that track dust storms on Mars and cloud belts on Jupiter. Professionals will also use the opportunity to recheck ephemerides, those exquisitely precise tables that say where a planet should be, because lots of eyes on one sky patch produce lots of positions that tighten tiny uncertainties. Expect noise online. You will see graphics with threads connecting planets into a spooky sigil. You will hear claims about energy portals or a coming shift. The antidote is a simple map. Draw the ecliptic, plot the ecliptic longitudes, and note the spread a few dozen degrees. That is a cluster, not a straight line. Then show a tide chart. The daily bulges track the moon above all, and the sun next. The parade is gorgeous. It is not a lever on Earth. There is cultural gravity here, though. Planetary gatherings were watched by ancient astronomers who saw meaning in conjunctions and omens in close approaches. You can nod at that heritage without importing the superstition. Use the event as a communal excuse to meet under the same sky. Schools can run pop-up star parties. Libraries can check out binoculars like books. City parks can turn off a few lights for 2 hours and gift thousands their first clear look at Saturn's ring. Hidden opportunities ride on the edges. When lots of telescopes point one way, serendipity increases. A faint new comet might sneak into those frames. A small asteroid might drift through, its motion tagged by accident. Even without surprises, the parade becomes a calibration frame for your own life. You will stand in a place you know your street, your field, your roof, and feel time in layers. The quicksilver flick of Mercury, the stately hold of Saturn, the in-between patience of Mars. If you want a 1-minute meditation on perspective, try this. Hold your hand at arm's length and cover Venus with your fingertip. Behind that fingertip lies a world nearly Earth's twin in size but hellish in climate, rolling under a lid of cloud thick enough to melt lead. Slide your finger to Jupiter. Under that nail sits a globe so vast that 1,000 Earths could tuck inside, banded with storms that have been rolling since before your great-grandparents were born. The parade compresses those distances into reach, then laughs gently as you remember what reach means in space. On the night of the chord, forget the arguments for a moment. Feel the aesthetic shock of a crowded ecliptic, then share it. Snap a frame, text a friend, point a kid at Saturn, and listen for the intake of breath. Planetary mechanics may be ancient, but this is a fresh chance to fall in love with them in public. The sky rarely hands you a group selfie of the solar system. When it does, make it count. Start with the easy magic trick. The moon does not change size, but its distance does. Its path is an oval, not a circle. Closest swing is called perigee. Farthest is apogee. When a full moon lands near perigee, it looks and feels bigger and brighter to our eyes. That is the supermoon. No cape. No cape needed. How much bigger and brighter are we talking? Numbers that matter to the senses. A perigee full moon can be roughly 10 to 13% larger in apparent diameter than an average full moon, and roughly 25 to 30% brighter in total light. Those are not abstract percentages. They are the difference between a white lamp and a whiter lamp that makes shadows feel crisper on open ground. Photographs taken months apart betray it cleanly. Your brain, which calibrates to the here and now, needs the side-by-side to admit the change. There is a second magic trick called the moon illusion. When the moon sits on the horizon, our perception engine treats it as larger because the brain reads it against trees, buildings, and mountains. Climb it high, and the illusion weakens. Combine real-size boost from perigee with the horizon illusion near moonrise, and you get a moment that feels almost theatrical. We do not have to speculate about psychology to enjoy the effect. We can measure the diameter in pixels when it is low and when it is high, and watch the number stay the same while our feeling does not. Tides are where the myths crowd in. A closer moon does mean stronger tides, but scale matters. Spring tides, when sun, earth, and moon line up at new or full, are already the high points each month. A supermoon can add a few centimeters to those highs. In places with marginal flood control or storm surge, a few centimeters can add up with weather to real nuisance. That is a planning problem, not a doomsday lever. As for earthquakes, the daily solid earth tide flexes the crust by tiny amounts all year long, with and without supermoons. Studies looking for a global bump in quakes during perigee fulls mostly find noise. If a fault is hair trigger ready, a tidal feather can be the last nudge. Most are not hair trigger ready on that day. Wildlife notices light. Nocturnal hunters that rely on darkness lose their edge during bright nights. Prey species stay tucked a bit longer. Shore creatures that cue to tide height and timing feel the supermoon's slight emphasis, along with the wind and pressure that already dominate their world. Humans notice sleep. Some people report restless nights during full moons. The more rigorous studies suggest tiny effects at best once you control for bedtime, screens, and noise. The brain is a storytelling machine. The calendar needs a referee. Now the joyful part, how to bottle the spectacle. Scout a foreground that means something to you. A skyline, a single tree on a ridge, a lighthouse. Use an app or an almanac to learn where the moon will rise and at what time from your location on that date. The closer you are to moonrise, the more foreground scale works in your favor. A long lens compresses distance and lets the moon loom behind your subject. A tripod, a remote shutter, and a quick practice the night before make everything calmer when the clock runs. If you want the walk on the moon shot someone silhouetted on a ridge, with the disk rising behind, stand a few hundred meters away from your subject and coordinate by phone or hand signals. Focus on the ridgeline. Expose for the bright moon, which will keep the person in silhouette. Try a rapid series of frames as the disk lifts, so you can pick the exact gesture you like later. It is theatre. With gravity for a stage manager, citizen science fits here too. With a modest telephoto and a stopwatch, you can help map brightness and colour under different haze and pollution conditions. Shoot a simple series at the same settings during several full moons across the year. Log humidity, temperature, and a quick note on air clarity. Share your images and notes with atmospheric groups that calibrate instruments using lunar light. Your pretty picture becomes a calibration source. The supermoon is also a neighbourhood night. Ask your city to dim a park for an hour. Bring binoculars for kids. Show them mares, the dark plains, and the radiating rays from bright craters. Ask them to trace the line where light meets shadow and imagine sunrise racing across a crater rim at hundreds of meters per second. The moon does not belong to astronauts or astronomers. It belongs to everyone who glances up when a white coin clears the rooftops. Keep one skeptical muscle trained. Claims will circulate about record closeness that is not, about guaranteed disasters, about secret agencies hiding the true numbers. The orbit is public. The timing is public. The physics is junior high trigonometry and a lot of patience. The truth is better than the fear. The brightest nights of a generation arrive on a schedule we can print ahead of time, and the biggest danger they pose is to the dignity of people who promised the sky would crack. So, step outside on the night, the moon swings closer, and let it be simple. Light on fields and faces, a sense that the familiar can still surprise you when geometry lines up. The same rock, the same craters, the same cold shines, but a little larger, a little brighter, enough to make strangers point together. That is not paranormal. That is the normal that feels like a gift. Hold this thought in your pocket for the rest of your life. In 2060, a visitor from the deep cold could turn night into a kind of silver twilight. Not for minutes, for weeks. Models suggest a giant from the far reservoir of comets might swoop inside Mercury's orbit and erupt so fiercely that it rivals the moon in brightness. Not guaranteed, not prophecy. A plausible forecast based on orbits already sketched and physics we trust. Start with scale. Most comets are dirty icebergs a few kilometers wide. The monsters that make history are tens of kilometers across, packed with volatile ices and dust that sunlight can loft into a world-sized atmosphere. When such a nucleus dives close to the sun, two things happen fast. Ice turns to gas at a phenomenal rate, and the escaping gas drags out more dust than any leaf blower you have ever seen. The hazy sphere, the coma, can swell larger than Jupiter. The tail can stretch hundreds of millions of kilometers, a luminous river written across the inner system. Brightness on the sky is not about drama, it is math. Astronomers use a scale where smaller or more negative numbers mean brighter. Venus at her best can shine near magnitude -5. The full moon hovers around -13. A truly titanic comet with the right mix of size, surface, and path could surge above -10. That means You will cast a shadow at midnight under a clear sky and read a page outdoors as if it were deep twilight. City dwellers would notice the difference through light pollution. Far from cities, the experience would feel otherworldly, as if the sky forgot it was night. So what makes this more than campfire talk? We have already met a near example in living memory. In 1997, Hale-Bopp became a household name by staying bright for months. It was large. It came close enough to light up and far enough to survive. It trained millions of eyes to look for tails without apps. The 2060 candidate is likely larger and is projected to pass closer. That is the recipe you would write if your only goal was spectacle. 2 caveats keep us honest. 1. Comets are fragile. Many begin grand and end. As heartbreak, thermal stress opens cracks. Jets torque the nucleus and spin it toward breakup. A slight change in how the surface vents can starve the coma and stunt the show. 2. Predictions far ahead carry error bars. The orbit math gets better with every new observation, but we should always say, out loud, that a forecast is a conditional bet. It pays out if the nucleus holds together, and if the path stays inside the sweet spot for heating but outside the death zone. If the dice land in our favour, the world becomes a planetarium without walls. You will see the comet grow night by night, not just brighter but bigger. The head blossoms from a star-like point into a cottony disk. A straight, needle-thin ion tail will point away from the sun like a compass hand. A broad, curved dust fan will flow behind along the orbit like a banner. Cameras will capture streamers and knots as the solar wind bangs the ion tail like a drum. It will not be subtle. Children born that year will carry the memory to old age. There are side effects worth thinking about now. Nocturnal wildlife reads light as a law. Predators time their hunts, prey time their hiding. A night source, as bright as the moon for weeks, would alter those dances. Human sleep, already fragile under screens and stress, might twitch at the edges. That is not reason for worry. It is reason to plan measurements. Ecologists could design global before and after studies that turn a scenic event into a once-in-a-century experiment on circadian biology. Park rangers could log behavior shifts. People could wear simple sleep monitors and contribute anonymized records. The comet becomes a natural laboratory while it dazzles. Safety questions always arrive with brightness. Impact is not on the menu. Orbits that give us a sustained brilliant display are, by definition, not bullseyes. Dust is another matter, but mostly as fireworks. When Earth later crosses the lane of particles shed by the comet, we could be treated to a bye. Meteor storm hundreds or thousands of shooting stars an hour if timing lines up. That is a gift, not a hazard, unless you count sore necks from looking up too long. How do you prepare for wonder? Begin by building the habits this series has been nudging you toward. Learn your horizon and a dark sight that you can reach. Practice low-light photography with a tripod and a fast lens so that when the sky ignites, you can capture it calmly. Teach kids the shape of the Big Dipper and Orion so they can feel the scale of a tail against familiar anchors. If you have a small telescope, tune it now, not then. A well-collimated instrument in quiet hands can turn awe into detail. Jets flicking from the sunward limb, a pale shell around the nucleus, faint ruffles in the dust fan. The scientific sprint will be joyous chaos. Spectrographs will dissect light to read the chemistry of ices from the deep freeze before Earth existed. Polarimeters will map dust grain sizes by how they scatter glow. Radio dishes will listen for the whisper of hydroxyl, a fragment of water molecules split by sunlight that turns comets into faint radio beacons. Spacecraft might pivot to watch from above the atmosphere. If a small interceptor mission is ready, parked in an orbit that can quickly pivot, it could dive through the coma and taste the vapor, banking samples of truth for a future that will still be arguing about how worlds first formed. Here is the tone I hope we set when the bright nights come. Excited, yes. Greedy for data, yes. But also generous. Invite neighbors who never cared about the sky. Organize impromptu sidewalk shows. Share simple tips so the first photo someone makes is not an overexposed white blob, but a frame that keeps the stars sharp and the tail delicate. Ore is a renewable resource that grows when spent. If the comet falters, we will learn why fragile things fail near a star. If it roars, we will spend a season living under a reminder that our solar system still throws punches of beauty without our permission. In either case, we win. The night might turn silver in 2060. Plan as if it will, and be honest about the if. That is how you meet the future with eyes open and cameras ready. Set a reminder you will never personally see fire. In the year 2177, Pluto will complete one full lap around the Sun since Clyde Tombaugh spotted it in 1930. One orbit. That is all. Almost 2.5 centuries to circle once. Everything we've argued about Pluto planet, not a planet, dwarf world with a heart-shaped glacier happened before it finished a single year. Why dwell on a date none of us will reach? Because it recalibrates your sense of time like a chiropractor for the mind. We live by heartbeats and school years. Planets keep books on centuries. Neptune, discovered in 1846, has just barely ticked past one of its own years. Uranus takes 84 Earth years to return to where it started. The outer system runs a clock that makes history feel like weather. Pluto's discovery story is a study in patience and persistence. Tombaugh, 24 and methodical, blinked pairs of photographic plates by hand, looking for a dot that shifted while the background stars stayed put. When he found it, the world cheered. A 9th planet from the American West. Later, better measurements and a wave of discoveries in the Kuiper Belt forced a cleanup of our categories. In 2006, astronomers drew a sharper definition of planet that Pluto did not meet. The public felt robbed. Schools fought over posters. Scientists debated like fans with season tickets. Through all of it, Pluto just kept rolling, not caring what we called it. Then New Horizons flew by in 2015, and silence turned to awe. The little world we demoted became a headline again, not because of labels, but because of landscapes. A nitrogen ice plain the size of a country with convection cells like boiling oatmeal, mountains of water ice floating like bergs, haze stacked in blue layers, and a sky that scatters sunlight softly at sunset. Charon, the big moon, revealed a fractured belt and a dark cap. Small moons whirled like dice. It felt like meeting a neighbour you had underestimated, and finding out they are an artist and an engineer and a mythmaker all at once. All of that naming fights and flybys fits comfortably inside the first third of Pluto's long year. That is the point. Our arguments are sprints on a marathon course. The orbit is the metronome. It says, take a breath. The research you start is a baton pass to someone not yet born. The archive you keep matters more than the headline you win. Science is one of the few human projects built to survive that kind of time dilation because it writes in a language anyone can learn and stores its memory in places strangers can open. So what happens at Pluto's birthday in 2177? No fireworks, no secret switch on climate, but the geometry will rhyme. Pluto will stand in the same patch of sky, relative to the Sun, where it was when Tombaugh's plates captured its first appearance. A patient team will produce a poster that shows the arc from 1930 to that date, dotted with all the discoveries we wedged into a fraction of one Plutonian year. Someone will read a passage from the old debates and chuckle. Someone will propose new categories for worlds we have not yet found. School kids will argue about whether Planet 9 is real in the same warm way kids once argued about Pluto. Think of the line this date draws back through us. People alive when Pluto was found watched humans step onto the moon, watched satellites build an invisible shell of tools around Earth, watched robots roll on Mars, watched the internet teach us to talk to strangers, watched New Horizons sail past a world beyond Neptune and send back postcards that made adults cry. Many of those people died before Pluto finished. Half a lap. The rest of us will hand the joy forward. A calendar that runs beyond a human life forces humility and invites continuity. Every long mission proposal, every data archive, every open code repository is a vote for conversations we will not finish. There is a deeper lesson hiding here, and it fits the theme of this documentary. Time is a variable, not a backdrop. Solar storms last days, comets write in weeks and months, planetary alignments strum at decades, supermoons remind you of monthly beats. Apophis gives us minutes in 2029 that bend an orbit for centuries. Pluto's year puts a marker in the far lane. When you see these scales laid end to end, the universe stops being a museum and starts being a city full of traffic moving at different speeds that somehow share the same streets. So do something small and concrete. Start a time capsule for the sky. Take a photograph of the region where Pluto sits this season, label it with date and place, and tuck it into an album or a digital folder with a clear name someone else can understand. Write a note to the person who will see 2177. Tell them what surprised you about Pluto, what made you smile when you saw the heart-shaped plane, what it felt like to hear people argue about names as if they were weather. Give them your laugh line and your best guess about what we will know by the time they open the file. When Pluto finally returns to its discovery longitude, the people on Earth will not be us. They will inherit our images, our equations, our mistakes, and our curiosity. If we do our job, the inheritance will be generous. The best way to honour a world with a year longer than nations is to build institutions and habits that outlast personalities. Pluto's first birthday since discovery is not our party, but we can bake the cake, light a candle on a memory stick, and leave it on the porch for whoever rings the bell. Let us turn wonder into a plan. You have just toured a season where the sun opened a magnetic gate, an interstellar comet slipped into shadow, another comet rose for backyard eyes, and a string of near-future celestial appointments lined up like a checklist. Here is how the next 90 days become a shared investigation instead of a passing headline. No waiting for permission, no gatekeepers, just a blueprint and a pack to stick with it. First, the Comet Watch cadence. Mornings belong to Lemon for 2 weeks. Pick 3 dawns you can actually make and put them in your calendar now. 2 hours before sunrise, open horizon to the east, binoculars and a simple log. Write down sky quality, rough brightness, any hint of colour or tail. If you can, add 1 quick phone shot through the binoculars on each morning. 3 consistent entries beat 1 dramatic selfie you never repeat. That log becomes your before for everything that follows. Then the vigil shifts to the evening glare, where 3-eye Atlas must reappear, or not. Carve out a small block on 5 evenings, spread across late October and the first half of November. You are looking low along the predicted path as the angle from the sun opens. Nothing on night 1 is not failure. A thin, straight needle of ion light may betray the return before the head brightens. If you see a candidate, freeze your settings and repeat the next clear opportunity. The sky tells its story in sequence. Give it the same camera, same exposure, same framing, so change is the only change. While you look, glance at space weather. You do not need a degree to read the 3 most useful numbers: solar wind speed, density, and magnetic orientation. Fast wind and a steady magnetic direction can write a clean, straight ion tail. Twitchy wind can yank and snap it. When your image matches the wind's mood, you will feel the physics in your chest, not just in a diagram. Next, assemble the tiny kit that multiplies your impact. A red flashlight to save your night vision, a paper star map or an offline app, so you are not glued to a glowing rectangle, a notebook with a pen that writes in the cold, a small tripod and a phone clamp if that is your only camera. If you have more, great, but do not wait for perfect. The sky rewards the ready more than the rich. Now recruit 1 friend in a different time zone, 1 high school science teacher who loves extra credit, 1 rural relative with darker skies. Share the handful of dates and the simple rules. Consistency beats brilliance. Timestamps matter. Label files sensibly. When the first whisper of a re-emerging comet appears in someone's stack, you will know because you will have a rhythm and a circle that can confirm rather than speculate. Fold in a science habit that professionals live by. Decide ahead of time what would count as a detection and what would not. For example, a point that moves the right distance along the right angle over 2 nights becomes a yes. A single frame smudge that vanishes under a slight change in focus becomes a no. Write those lines in your notebook before you start. When the adrenaline hits, your past self will save you from inventing rules that flatter your hopes. The next 90 days are also your training arc for the bigger appointments we mapped. Apophis will demand calm technique, not new gear. The 2040 planetary chord will reward habit, not hype. A mega comet, if our luck holds in 2060, will lift those same muscle memories onto a larger stage. You are not practicing for nothing. You are wiring the skills you will use when the whole neighborhood looks up and asks you where to point. End with a pact. We will use wonder to pull more people into measurement. We will be loud and generous with raw frames, and quiet and rigorous with claims. We will not let conspiracy eat attention we could spend on good questions. We will give credit, like water, and correct mistakes like surgeons. We will take care of dark places as if they were sacred, because they are. The night sky is not. A backdrop. It is the commons where our species remembers it, shares a roof. When the next whisper arrives, a faint needle near the sun, a tiny second point along an orbit, a sudden green bloom in a backyard frame, do not just feel the thrill. Package it so someone across the world can test it. Names are nice. Proof is immortal. That is how you go from spectator to collaborator and from collaborator to ancestor. The first chapter of this story opened with a hole in the sun and a vanishing interstellar traveller. The next chapter opens with you, bundled against the cold, logging the sky like a patient detective. Pencil ready, eyes up. Let us keep watch. Take one last look at the map we just walked. A hole tore open on the sun and reminded us that space has weather. An interstellar ice relic slipped into the glare and dared us to keep watch. A homegrown comet rose for sleepy eyes at dawn. Physicists stitched a whisper line of light across continents. Biologists taught yeast a new trick. A fish yawned and tugged at our theories of minds. A mountain named Apophis will skim our sky. Planets will crowd the stage. The moon will swing close. A mega comet might turn night to silver. Pluto will finish a single year and mock our hurry. All of it is one story about attention. So here is the question the sky is asking. Will we be tourists, or will we be residents? Tourists point once, snap once, move on. Residents learn the seasons, the shortcuts, the neighbors' names. Residents fix things. Residents build. To be a resident under this roof means treating wonder like a starting line. It means we learn just enough craft to turn goosebumps into good notes, and good notes into shared knowledge. That begins small. You save a clean copy of your best frames and your honest misses. You label them with time and place. You write a sentence about what you thought you saw, then a second sentence about what later checks proved. You share both. The humility in that pairing is rocket, fuel. It tells your future self to be brave and careful at once. It lets strangers trust you when the next bright thing arrives and the internet fills with claims. Then you widen the circle. Invite someone who has never cared about the sky to look through your viewfinder. Let them press the button. Text them the picture. Show them how the same patch of darkness changes from night to night. Tell them that the camera is not magic. The patience is. People fall in love with what they help to measure. If enough of us share that feeling, dark places will be defended. Light pollution will be treated like waste instead of wallpaper. And every kid within a bus ride of a park will see Saturn's ring at least once before they are grown. Keep your skepticism tuned like an instrument. When events collide in the headlines, breathe and check the calendar. When a theory offers thrill without risk, ask it for a prediction you can test. When someone shouts that the sky is falling, ask them for the coordinates and the time. The cure for noise is not silence. The cure is signal. Signals come from checklists, repeats, and friends who are allowed to tell you when you are wrong without losing your warmth. Also, keep your joy. The point of knowing how tails disconnect or how quantum keys bruise when touched is not to be clever. It is to feel more alive when a thin blue needle appears near the sun, when a bright rock crawls over your neighborhood, when a small fish reminds you that minds are wide. Knowledge makes awe last longer. Awe makes knowledge worth the late alarm and the cold hands. There is work ahead. In the coming weeks, Lemon asks for 3 mornings. Atlas asks for 5 evenings. After that, the calendar keeps handing us reasons to gather. The parade in 2040, Apophis in 2029, the silver nights that might arrive in 2060, Pluto's long joke in the 22nd century. None of these needs permission from us. They will happen. What changes is but whether a generation remembers them as rumors or as things they touched with their own eyes and notes. So here is our pact, one last time, said out loud. We will trade rumors for logs. We will trade hot takes for cool exposures taken twice. We will trade lonely amazement for invitations. We will treat corrections as gifts and credit as currency. We will ask better questions next month than we asked this month. We will protect the commons above our heads by turning strangers into residents until a city night sky is once again a place where Orion is a friend and not a myth. If this chapter lit a fuse in you, carry it forward. Join the watch. Share this film with someone who only sees the sky through windows and wires. Subscribe so the next alert lands in your hands right when the first whisper arrives. Leave a comment with your city and your sky and the one thing you want help learning next. These are not vanity metrics. They are how a scattered crowd becomes a network that can catch a faint returning comet and tell the world that it is real. The sun will open again, the comets will come and go. The ground will shake somewhere, and we will argue about meaning until the data calms us down. Between now and then, the night waits for you to step outside, tilt your face up, and add one careful line to a long-shared notebook. That is the whole game. That is how you turn a viral story into a living practice, and a living practice into a legacy. The roof is wide, the door is open. Bring a jacket, bring a friend, bring a pencil. The sky will do the rest.